Okay, let's now handle the third product rule. Suppose you have a constant or a scalar C is equal to x transpose y. X is a function of another vector z, and y is also a function of the same other vector z. And I want dc by dz as a vector. Now we know that this is really equal to partial c by partial z1, partial c by partial z2, up to partial c by partial zn as a row vector, of course assuming that z is equal to z1, z2 up to zn. Now we want to get this vector. So at first, let's see this quantity. What is c? C is equal to x transpose y, which is really equal to x1, y1 plus x2, y2 up to xn, yn. So this is sigma xi, yi from I equal to 1 up to I equal to n. Now I want the derivative of this with respect to z1 and z2, and in general I want partial c by partial zk for any zk. Now this is equal to partial by partial zk of the summation sigma xi, yi. Then this is equal to the summation of partial by partial zk xi, yi. Now this is the product of two scalars, so I can apply the original product rule or the scalar product rule. So this is equal to sigma of xi partial yi by partial zk plus yi partial xi by partial zk. Again, we can write this as two summations. The first xi partial yi by partial k over I, so k is a constant while I is our iterator here, plus another summation over I of yi partial xi by partial zk, and this is partial c by partial zk as a scalar. Very well. Now this first term can be written as x1, x2 up to xn as a row, multiplied here by a column. This is a dot product also, so this is multiplied here by some column. This column has here partial y1 by partial zk, so this is zk, partial y2 by partial the same zk up to partial yn by partial zk, right? Right. Now the second right here is also a dot product between y1, y2 up to yn multiplied by some column here, which is partial x1 by partial zk, partial x2 by partial zk up to partial xn by partial zk. So this is the second term. Now I want to put all those derivatives next to each other, and so I can see that partial c by partial z1, partial c by partial z2 up to partial c by partial zn is really equal to, here I have again x1, x2 up to xn. Now for this first one I need here partial y1 by partial z1, then partial y2 by partial z1 up to partial yn by partial z1. So that's for the first term. And here I can have a similar term y1, y2 up to yn multiplied here by the first column here, which was partial x1 by partial z1, partial x2 by partial z1 up to partial xn by partial z1. So that's for this first term right here. Now for this second term, I need to have a second column here having partial y1 by partial z2. Because of this, here I have partial y1 by partial zk for any zk I want. So I hear partial y1 by partial z2, then partial y2 by partial z2 up to partial yn by partial z2, and I can continue for all the remaining terms. Here also I have partial x1 by partial z2, partial x2 by partial z2 up to partial xn by partial Z2, and again I can continue here and here and here. Now it's clear that this is really equal to, here I have X transpose, here I have a matrix. Remember that a row multiplied by a matrix will give you a row, just as expected here. So now I have X transpose multiplied by a matrix. The first row of this matrix is really the gradient of y1 with respect to the vector z. The second row is really the gradient of y2 with respect to the vector z, and here I have up to the gradient of yn with respect to the vector z. Here also I have y transposed multiplied by another matrix, here having the gradient of x1 with respect to z, so gradient with respect to z. Here I have the gradient of x2, x2 is a scalar of course, with respect to z. Here I have the gradient of xn with respect to z. Now, if you look at this matrix is really a Jacobian matrix. This is the derivative of the vector y as a vector with respect to the vector z, here multiplied by x transpose, plus y transpose multiplied by another Jacobian matrix, which is the derivative of the vector x with respect to the vector z. Very well, so this is our final conclusion. The derivative of x transpose y with respect to z is really equal to x transpose dy as a vector by dz as a vector plus y transpose dx as a vector by dz as a vector. So this can be thought of as our third product rule. So let's put it inside a box here and have this as the third product rule.